Let's see, what are they doing? This girl laughing is named Amniyah Nur Syahmina. This girl walking elegantly is named Syakirah Khairuddin. This girl name is Aimi Shasha. This guy here is Dzaffer Rasyadd. And this girl standing here doing nothing is Baiq Afiqah.
The rapid advancements of digital technology has led to an increasing demand for electrical energy to power personal and industrial electronic devices. Traditional energy sources are limited, therefore it creates an urgent need for innovation of sustainable energy utilization. Humans move around a lot, whether it's chasing the bus, running into classes, or even have a job. But thus, all of the movements are beneficial. Let me pass this to my friend.
Actually, it can. It is called piezoelectronic. Piezoelectronic converts mechanical stress into electrical energy through piezoelectric materials. This approach aligns directly to United Nations Sustainable Development Goals SDGs, particularly SDG 7, SDG 9, and SDG 12. However, the major problem is that the government is only focusing on major scale projects. So, we decided to create a micro-energy harvesting material, which is the piezoelectric keyboard. Now, this overall increases and maximizes the usage of sustainable energy, all the while reducing energy waste.
Now, I'll be explaining about the methodology for this project. For the materials and instrument, this is what we need. For the procedures, first, the keyboard is disassembled to attach piezoelectric disc under the keys. Second, the piezoelectric disc is attached under a selected keys to convert mechanical pressure to electrical energy. The selected keys are W, A, S, D, Enter, backspace, and a spacebar. Third, all the piezoelectric disc is connected in a series circuit to ensure all the discs is in the same circuit. Fourth, the piezoelectric circuit is connected to a capacitor to store the energy temporarily. Fifth, the output of the capacitor is connected to a Type-C charger to transfer electrical energy to external devices. Lastly, the Type-C charger is connected to a power bank to store the harvested energy. For the data analysis, a multimeter is used to check the actual voltage generated by the piezoelectric disc.
Now I will present the results, expected outcomes and challenges of our project. Based on our theoretical analysis, we expected that the piezoelectric keyboard can convert mechanical energy from key presses into electrical energy. We also expected that higher applied force and longer pressing duration would produce higher voltage output. However, the energy generated is very small, so the system is only applicable for low power applications such as LEDs and not for larger devices. The actual results, we observed the same trend. Low pressure produced low voltage, while high pressure produced high voltage. Similarly, increasing the duration of key presses also increased the voltage output. This happens due to the piezoelectric effect, where mechanical stress on the material generates electrical charges. However, even though the voltage increases, the overall energy remains low because the current produced is small. In the project, we faced several challenges. The energy output was too low for practical use. The placement of piezoelectric disc was difficult, and inconsistent typing force causes fluctuating results. Also energy losses in the circuit, and the discs were fragile. In conclusion, the system successfully demonstrates energy conversion, but it is more suitable to be used as demonstration or educational use rather than a large-scale system or energy applications. Thank you.
So, in conclusion, our project studied how piezoelectric materials can be used in keyboards to turn our typing energy into electricity. We also tested how different conditions affect the power output and looked at its environmental benefits, aligning the important sustainability goals. Overall, our project shows that piezoelectric keyboards can help save energy and also support to a greener future.